we're going to talk about how you find area in polar form. So to start with, we're going to go back to a circle. If we have a circle and we want to find the area of a sector of that, what do? Well, we know how to find the area of a whole circle. Area of a whole circle would be pi times radius squared, whatever this radius might be over here. But if we're only finding a portion of that, we'd only want that percentage. And we can find the percentage by using the angle. So if it was in degrees, we take whatever this angle theta is and find it as a percentage out of 360 degrees, since 360 is the number or distance around the angle when you're in degrees. So that's how you'd find it if you were in degrees. If we change that to radians, then that becomes, instead of the angle over 360, it'd be the angle over 360 degrees is the same as 2 pi in radians. So in radians, the equation will look like this. Well, we can simplify this radians one out a little bit. If I cancel out these pi's and move this pi out of the numerator, the equation then becomes, I got to put some on the top of that fraction now, so 1/2 angle times radius squared. And that's how you find area of a sector of a circle. And we're going to use something similar today when we're working with polar form to find area of a part of the area of one of these polar graphs. So when you are graphing in polar form, recall that you have some starting angle here. Let's say it's A that you start at. That gives you that starting pole. And then your angle rotates counterclockwise out to something. And when you do that, whatever that function might be carves out some graph or some picture here. So if we want to find the area covered by that, what we're going to do is use that same area of a sector equation and use it with an integral here. So if we take that 1/2 radius squared times theta equation, and we're looking for the change in area here, that also means we'd be finding the change in our angle here. Also, we just changed r to f of theta here, since it's the same thing. That would give us one of these little sectors here. So if I change this to now a summation of all of them, if I just take one here, like this one, to the next change in theta, that would give me this graph here, and I'd get this shaded region in here. Well, that's not exactly what we're looking for, because we want that area under the curve, and this goes outside our curve, and we get some empty space there. But if we take that same idea and find the find all these areas from the starting point out here to the ending point, we can do that, and that would give us all these. But again, we get these ones where we're not quite getting maybe all the exact angles. Well, if we take the limit as the number of those sectors goes to infinity here, that would then give us the exact area under that curve. And if we write that in integral notation, it would be the integral from a to b of 1/2 times our function of theta squared d theta. And if we just change f of theta back to our r notation, it ends up being 1/2 radius squared d theta. So this is going to be now the way we find area in polar form. That's the integral you're going to want to use and know. Let's try that on a problem here. So find the area enclosed by one loop of the 4-leafed rows you would get by graphing out this polar function. Okay, so we want to create an integral here to find our area. Area is going to be the integral from a to b of 1/2 radius, or our r function here squared, d theta. All right, so what's our starting and ending one? Well, we got to see, where does this begin? What if we were to put 0 in here? So if we were to do 0 as our angle, what would that be? Well, you'd end up getting cosine 0, and cosine 0 would be 1, so r would be 1. So it looks like the starting point would be right here. That's when theta equals 0. You can also see this if you were to graph it out. Let's graph this out and see what it looks like. So on the calculator, go to your mode. Make sure you're in polar form down here, which mine's already in. So you want to make sure that it's not in function or parametric, but you're in polar. Then let's go to our r equals equation, type this one in. So we want to graph out cosine 2, and if you're in polar form, when you hit your variable button, it should be theta here. And let's graph this one out. I'm going to go zoom. Let's go number 4, decimal 1. So you can see there it is. And as this was going here, you could see that it started here, and that graph was moving this way. And at pi over 4, it ends up being there. You could also see this by going to table on here. And if you put in the correct table value, you would see that at pi over 4, it is going to be 0 here. I'm going to change my table settings here. Let's go up by pi over 4. If I go back to my table now, I can see, yeah, at pi over 4, the r value is going to be 0. So if we were to just graph from 0 here, that would start us right here. And as we are moving to pi over 4, then, like, if I just graph from here to here, that would give me this area. If I just graph from 0 to here, now that gives me this area. And if I keep going all the way to pi over 4, that would give me this whole area of just half of that petal of this 4-leaf clover. So we could come up with the area of this one by doing the integral from 0 to pi over 4 of 1/2. Our r in this one is cosine 2 theta, and then it's all that squared d theta. But that would only give us half of this petal. They want, what's the area of one loop? So if we want the whole loop, we could just take this then and double the value. So if we did 2 times that, that should give us that area. So now what we want to do is solve this out. And you could do this by putting it in your calculator and helping you find it that way. You could easily do a little bit of simplifying here too. If we moved this out here, it looks like half of 2, that's just going to cancel. And so now this just becomes 0 to pi over 4 of cosine 2 theta squared d theta. I'm going to enter that one in the calculator. Let's see what we get. So I'm going back to my main screen here. Let's go math. Let's go do our integral here. We're going to do it from 0 to pi over 4. And then our function here is, I'm going to start a parentheses here, cosine 2 theta, close that up. Here also I want to close up that cosine one I started, square that, and then out here d theta, and if we enter that, should give us the answer. There's our answer. Now this might seem random here, but remember, oftentimes when this is going on, it's part of like a curved, which is part of like a circle. Let's just divide this by pi and see if part of this is talking about pi. And it looks like it is. It looks like pi is part of this answer. If we change this to a fraction here, you get 1/8. So it looks like the exact answer here comes out to be pi over 8 would be the exact area. That may not always work, but you should kind of check when you're doing these if pi is part of the exact area. Otherwise, you could approximate.